Hello again, Physics 243. In this unit, we'll discuss the Doppler effect. Now, I'm sure that you've heard of this, and actually, if you haven't heard the name, I'm sure you're familiar with the physical phenomenon. So the Doppler effect occurs when a source of sound moves with respect to an observer. I think all of us have experienced a truck driving by, and you hear the siren, and as it goes by, the pitch drops. You hear something like that. Okay, that's the phenomenon. A stationary observer, these people here are stationary, and here's this truck. Stationary observer hears a fire truck siren change in pitch as it drives by. Okay, so in this unit, we'll analyze that phenomenon. Okay, so let's consider a fire truck that's at rest. It's not moving. And two observers. One's over here at rest and one's over here at rest. Okay, so these guys detect the same frequency, right? I should have said also that the fire truck is emitting sound waves. It's got a siren. So the sound waves are coming out. And let's say it's a siren. It's just a tone. To make it easy, let's just say it's a tone at a certain frequency. And the sound waves are coming out, and here are the wave fronts of the sound waves. Okay? You could think of this as the region of greatest pressure or greatest compression of the molecules. And that's propagating outwards in both directions. And upwards too, but I didn't draw that. Okay, so these observers, everything's at rest, and these observers will detect a frequency, and they'll measure the same frequency. Right, just with the sequence. This is what's called the frequency of the siren. Now suppose that the fire truck moves. Look what happens to the wave fronts. In front of the truck, the wave fronts bunch up. That's simply because after emitting one wave front, the source of the sound in the fire truck moves towards that same wave front and then emits another one. So by that way, these wave fronts tend to bunch up in front of the source of sound. And as a result, the observer who's here on the ground at rest receives more wave fronts per unit of time than she did when the truck was not moving. Right? So she will detect a higher frequency and a shorter wavelength. Right? You can see from the picture that she's receiving more wave fronts per second than when the truck was not moving. Now, if you look on the other side, notice that the wave fronts are farther apart, simply because when the truck emitted this one, it then moved to the right before emitting the next one. And so they're farther apart than they were when the truck was not moving. So this observer detects a lower frequency and a longer wavelength. So it's a pretty simple idea that underlies the Doppler effect. But actually it can be quantified. By the way, the same thing happens if the truck is at rest and the observers move. So let's assume that this observer moves this way. It could be that she's running, but more likely she's in a car driving towards the fire truck. And let's say the fire truck is at rest. Well, since she's moving, she will encounter more wave fronts per second than she did when she wasn't moving. She'll just run into more wave fronts per second. Right? Person encounters more wave fronts per second when moving towards the truck than when standing still. So therefore, she would measure a higher frequency. And now, similarly, if this guy moves away from the truck, that person will encounter fewer wave fronts per second than when moving away from the truck than when standing still. Because when it encounters this one, it then the observer moves to the left a little bit before the next one catches up with it. So fewer wave fronts per second. And so that observer, when moving away from the fire truck, will measure a lower frequency than the siren's frequency. All right. So it can be quantified, as I said, with some analysis, which I can do in a separate recording. But it's called the Doppler effect. Suppose that F is the frequency of the sound emitted by the source, as measured when the source and the observer are stationary. The fire truck is not moving, the observer is not moving, observer measures the frequency of the sound of the siren. Right? That's F. Now suppose that the sound source and or the observer moves. Right? So this sound source could move right or left, and the observer could move right or left. And F prime, let F prime be the frequency that's measured by the observer. Right? One more thing we need, and that is let V sub sound. V sound is, let that be the speed of sound. So V sound is the speed of sound. And here it is. The frequencies are related by this formula. This is the Doppler formula. Now you have these funny symbols inside, inside this fraction here. So the way you use this formula is subject to these rules. The upper signs, meaning the positive here and the negative here, the upper signs apply if the source and or the observer move closer together. Right? So the source could be moving towards the observer, and or the observer could be moving towards the source. Right? Then you would use the upper signs. You use the lower signs if the source and or observer move apart. All right. So that would be the minus sign up here, or subtraction, and a plus sign in the denominator. All right, let's do a simple example, the standard one. This time, though, it's a police car. So the siren of a police car, which is at rest, emits a predominant frequency of 1600 hertz. So as we've said so far, sounds have a mixture of overtones, but there's usually one predominant frequency, and that's the pitch that you perceive. We're being told that that predominant frequency is 1600 hertz. What frequency will you hear if you are at rest and the police car moves at 25 meters per second, either towards you or away from you? All right. We need the speed of sound, so let's look that up, and let's use 343 meters per second. So that was the speed of sound. I think it was at 20 degrees Celsius and standard atmospheric pressure. All right, so in part A, you and the police car are moving closer together. So we use the upper signs in that formula. Here they are. With the plus sign and the minus sign like this. So what are the things that we have in here? Well, the observer is at rest. You are the observer and you are at rest according to the problem. So your speed is 0. The speed of the source is given as 25 meters per second. That's the car moving. And then the frequency of the siren is 1600 hertz. The other pieces of speed of sound, which we put up here. So that's it. Just plug in the numbers like this. Put that in the calculator and you get 1726 hertz. So when the police car is moving towards you, notice that you hear a frequency that's higher than if the car were stationary. Part B is what if you're moving apart. In that case, you use the lower signs in the same formula. So it looks like this. Now you have a minus sign here and a plus sign there. All the numbers are the same. The observer is 0, the source is 25, and frequency is 1600. Same speed of sound. So just do the same calculation with those different signs. And this time you get 1491 hertz. So when the police car moves away from you, you hear a pitch that's lower than the frequency of the siren if it were not moving. All right, so as the car approaches and moves past you, you hear the siren drop in pitch, which I think most of you are familiar with. Specifically, we can calculate it. It goes from 1491 hertz to 1726 hertz in this case. All right, so next time you hear a siren go by, I would like you to remember fondly your physics class, because we calculated the Doppler effect. Okay, another example, and it's an interesting case. A bat. So you know that bats echolocate. So assume that the bat at rest. So we're going to assume the bat is at rest. So bats usually fly around. It's a little easier if we assume that the bat is at rest. And the bat sends out an ultrasonic sound. Sends out ultrasonic sound waves at 46.5 kilohertz. And then the bat receives them returned from an object that's moving directly away from it at 31.5 meters per second. What is the received sound frequency? That sends out waves at 46.5 kilohertz and then receives the reflected waves at a different frequency, and we have to find out what that frequency is. So we use the formula, and in this case, we have that the object is moving away from the bat, so they're moving apart, and so we're going to use the lower signs, minus up here in the numerator, plus in the denominator. Right? We have the bat at rest. There's a wave coming out. The object is moving away from it. That frequency of the emitted wave is 46,500 hertz. Right? That's what the kilo means. Frequency received by the object is this, with, as I said, with the lower signs from the formula. Notice that this source has a speed of 0, and the observer has a speed of 31.5 meters per second. Plug in the 46,500 hertz here, and the end result is 42,229.6. Probably too many significant figures. I'd round that to maybe 42,200 hertz. Okay, now we haven't finished. This is the frequency that is received at the location of the object. Right? The object is moving, and it will receive wave fronts from the bat as it moves at this frequency, 42,200 hertz. Those wave fronts then reflect off the object and go back. So essentially, in fact, literally, the object is now sending out sound waves at this frequency, 42,200. Those sound waves are the ones that are bouncing off the object. So now we have to do the Doppler effect all over again, because the sound bounces off the moving object and returns to the bat. In this case, we have a moving source and a stationary observer. So it's the same formula, and once again, they are moving apart. So once again, we will use, right, so the waves are now going the other way, but they're still moving apart, so we'll still use the lower signs. And the frequency f that we plug in is going to be this. So my notation is then going to be like this. So f double prime, right? The single prime is the Doppler shift, and then the double prime is the doubly Doppler shifted signal, right? The single prime one is going to act as the source of the sound waves reflecting off the object, and then it'll be received at the bat at a frequency f with double prime. Okay, so now the speed of the observer is 0, and the speed of the source is the 31.5 meters per second. See, the numbers entered the formula in a reversed order in this case. Okay, plug in the 42,229.6 hertz here, and you'll get 38,677.6, which I would round to 38.7 kilohertz. Okay, so we had to do 2 Doppler shifts, right? The bat sends out the sound waves, and the object receives them at a Doppler shifted frequency, but they also reflect off the object at that same frequency. So then we do another Doppler shift because those waves are emitted by the object and then received, which is moving, and then it's received by the bat. Okay, so it had to be had to use the formula twice in this case. So the bat gets information about the object. For example, the object is probably an insect. Right? The bat could have some information about how far away it is, and that comes from simply the time that it takes the signal to return. Now, we didn't calculate that in this problem, but we did it in an earlier time at the semester. Right? So bat can figure out how far away it is just judging the time that the signal took to return. But also, now with this Doppler information, the bat gets information about which way the object is going and how fast it's going. Right? That information comes from the Doppler shift. It's pretty interesting, right? Okay, so the first of these receiving information about how far away it is by measuring how long it takes for a signal to bounce off an object in return. That's the basis of sonar, which stands for sound navigation ranging. So this is a way that you can locate things underwater. If you have a boat, you might be able to use this to locate the bottom of the lake so that you know how deep it is. But the same technology is used in geology to understand, the structure of the geologic strata beneath us, and also if you're looking for oil, for example. What they do is they do a controlled explosion, and that basically causes a sound wave to go through the earth, and then it gets reflected by various things, and people can analyze those reflections and decide where there's rock and where there's maybe water or maybe oil. That's simply just the reflection and measuring time. But the method is also used in medical applications in combination with the Doppler effect, the way we just saw with the bat. So the emitted and received signal can be mixed, and because they're shifted in frequency, we'll get beats. And so the frequency of the beats contains information about the movement of the thing that you're interested in. So for example, you could monitor the location of a fetus inside the mother. Monitor the movements of the fetus, right? Because the Doppler information tells you something about how the fetus is moving, and in particular, the heartbeat, right? Heartbeat, there's some tissue moving when the heart beats, and you can actually measure that using sonar. Essentially sonar, right? Usually it's called ultrasound in the medical, in the doctor's office. Okay, so I hope you enjoyed this. Next up, I'll do a derivation of the Doppler formula, but that's optional. I'm not going to test you on that. But I do want to offer you some information about where the Doppler formula came from. Okay, hope you enjoyed this. See you in the next one.